a biology class. When I was taking biology classes during my growing up years, every class, not one class they did not talk about evolution. So let's just say a few things about it, not a whole lot, but a few things about it. And I did talk about it throughout the semester. Is that right? We talked about endosymbiosis. You guys remember that? What is endosymbiosis? Excuse me. What is endosymbiosis? Anybody remember that from previous exams? Endosymbiosis, it was when you had a big cell and you had a small cell, like mitochondria. The big cell engulfed the small cell, and the small cell, which was a prokaryotic cell, this is an eukaryotic cell, endosymbiosis. Okay, endosymbiosis was when a chloroplast, remember, thylakoid, this would be a bacteria. This is also a bacteria. Of course, these are all theory. When it went inside of the cell, now that bacteria did photosynthesis for that cell. This bacteria did cellular respiration. And the name of that process is called endosymbiosis. We talked about it at the beginning of the semester. But that is an evolution. Again, it's a concept of evolution. Population and evolution. The definition of a population is interbreeding group of organisms, one species that occurs in a given area at the same time. That's the best definition for population you're going to get anywhere. Definition of a population when you have a group of same species that they can breed and they can have offsprings, that those offsprings can multiply also. What is the answer to this question? When you cross horses with donkeys, right? What do you get? A mule. Can mule reproduce? So horses and donkeys, is that a good example of a population? No. First of all, they're two different species. Horses and donkeys, you can cross them, yes. They will have offspring, yes. But their offspring is not able to reproduce. So that is not a good population. Horses and donkeys is not a good population. Anyhow. Synthetic theory of evolution says that Darwin theory of evolution and science of genetics and Mendel, when you put the ideas of the Mendel and you put what Darwin put together, that came up with a new, they call it new Darwinism, which is the synthetic theory of evolution. Synthetic theory of evolution is when you put Darwin theory, which I will talk about it here in a minute, and Mendel's laws together, that is called synthetic theory of evolution. Darwinism, what did Darwin say? Darwin said organisms produce offspring similar to themselves. That's a fact. Okay? You have some exceptions. Horses and donkeys, they make mules, and mules is not same. And also, he said, within a population, there is a variation. Do you want to sit here? I want to sit in your way. Within the population, he noticed that within a population, there is a variation. There is a variation among them. Is that right? In this room, we have a population. We can breed, and we can have offsprings, and those offsprings in this room can breed also. Okay? However, within this population, Darwin noticed that the organisms are different. Okay? The females are different. The males are different. That's what he noticed. He also noticed that survival members are small in a population. He's not talking about the number of the offsprings that survive. He was talking about the number of the eggs and sperm survive. In case of human, let's look at it. You were born, all of you in this room, were born females. I'm talking about the females. You were born with about 1 million eggs, roughly. By the time you reach puberty, you have only 500,000 eggs. The numbers are different in different textbooks. You have 500,000 eggs, and by the time you will not shed any more eggs, which is age 55, 60, how many eggs do you think you shed in your life? One each a month, right? After age 9, subtract 10 from 55, is that right? That is 55, that's 10 minus 55 is 45, 45 times 12, it's roughly about 500. Do you have 500 children? Does anybody in the world on planet Earth has 500 children? So the number of the eggs, the survival numbers of the eggs in a population is small. Natural selection, survival will withstand environmental pressure. But what he proposed that HIV comes, you already know about HIV, we talked about it a little bit. HIV will come and wipe out a lot of population. A few of them survive. Those few that survive in a population, a few that survive HIV, most like female and male, most likely, what do you think? Do you think their children will also survive HIV or not? Yeah. And that's what natural selection is. Natural selection is diseases, predator, environmental pressure. Anything. Water, fire, weather, whatever it is, that's called natural selection, environmental pressure. Okay? So environmental pressure could be a tiger. If a tiger chased all of us in this room and eat all of you, 2 of us survive. 2 male and female survive. And then most likely our baby can survive from tiger too. Can run fast. Is that right? That baby maybe, not necessarily, maybe can survive also because the parents survived the tiger. That could be a disease as well. Yes?
Is that what happened in like Kenya and Ethiopia? Like with runners? Like Kenya and Ethiopia?
Well, they're not running from tigers, but yes, that's what they're saying. The gene is within them, possibly, so they have marathon runners. Yes.
Yeah, that's what I'm saying.
Yes, marathon runners.
Because like back in the day, they used to chase down their food on foot and stuff. Like, is that why, like, over hundreds of years, like, they have better genes for marathon running?
I don't know much about it, but if you can research it, yes, and let me know for your zoology class you take next semester. That would be your topic. Okay, population evolves and not individuals. That's another thing. Before Darwin, like Lamarck, who proposed, Lamarck talked about evolution. What other people before Darwin mentioned evolution, they were talking about individuals. Individuals evolve. But Darwin came and said, no, individuals did not evolve, population evolved. Okay? That was the big difference between Darwin and Lamarckism. Lamarckism, do I have it down? I should have it. Lamarckism, you will see it. Lamarckism is, Lamarck came and said, individuals evolved. The giraffe long neck evolved because the food was on top of the tree. But Darwin came and said, no, the giraffe neck evolved because of the population evolved. It was not just because one giraffe long neck evolved. But anyhow, I'll come back to that. Gene pool is total of all of the alleles of all of the genes of all of the individuals in a population is called the gene pool. In this room, we have a gene pool. Of all of our alleles, all of our genes is called the gene pool. Is the gene pool of this classroom bigger or the gene pool of a mountain house? Which one is bigger? The gene pool of this classroom is bigger or the gene pool of mountain house? The city of mountain house. I don't know, is it city yet? It's a city. Is mountain house gene pool is bigger or city of Stockton? City of Stockton gene pool is bigger. Okay. Okay? If gene pool does not change, the following must occur. It means when the gene pool does not change, it means all of the people in Stockton stays put, they do not migrate out, or nobody migrates into the city of Stockton, nobody migrates inside of this classroom, let's take it smaller, and nobody leaves this classroom. The following must occur. That's what they are. Mating must be random. Okay, within a population, mating is random. Okay, and all alleles must be equally viable. All alleles must be equally presentable to the population. Population must be large, of course. The gene pool does not change. It does not work for us in this classroom. But individuals cannot move in and out. That's something I talked about that. Okay, so those are the criteria for having a gene pool. Population and evolution. Okay, that's the next thing. I said all of that to come up to this one, population and evolution. Hardy-Weinberg, there were two mathematicians. There are two mathematicians that they came down with this equation that explains evolution a little bit better. And I'm hoping you would know this because in zoology I will not go over it anymore. I just continue on Hardy-Weinberg and keep going a little bit more. What it is, if P plus Q, and I will explain what they are in a minute, hang on. P plus Q is equal to 1. And during the exam, during your final next week, I give you a problem like this, and then you have to do it without calculator. You have to solve the problem. Let's go over it. So together, stay with me. So P plus Q is equal to 1. You all had math, and you know in math, they try to prove the equation for you first. So that's what I'm doing. First, I'm trying to prove the equation for you. And then we'll talk about some diseases, some genetic disorders, and how this equation can be used to predict what the population have as far as that disease. But anyhow, capital A dominant allele, you already know that. Small a recessive allele. And let's say capital A is equal to P, and small a is equal to Q. And in that population, the capital A is 80% of the population is capital A. 20% of the population, same thing. Small a, 0.8 plus 0.2 is equal to what? 1. Equal to 1. Okay? So, P plus Q is equal to 1. We already said that. Or, can I say this, math? 1 minus Q is equal to P? Or can I say 1 minus P is equal to Q? Are all of those right statements? Are all of these right statements? Huh? Yes. Last time I checked my calculator, they're all right. Okay, now, what is the probability of the double homozygous dominant? You remember this? We talked about this. Big A is homozygous dominant. Big A, homozygous dominant. And small a, homozygous recessive. And then capital A, small a, 3 possibilities, right? Heterozygous. Heterozygous dominant. You all remember that? Okay? And then, that's what I wanted. In a population, how many people are not carrying a gene? How many percent? How many percent are having the disease? And how many people are carriers? You remember this? We talked about this. The people in a population that have this, they are the carrier. These people have the disease. And these people do not have it at all. They are not carrier. They are healthy and they are not carrier. These guys are healthy, but they are carrier. They are carrying the gene. If they get married to another person just like themselves, then they can have offsprings like that. Do you remember that? We talked about all of this. Okay? So, what am I saying? What is the probability of capital A, small a, capital A, small a? It is 0.8 times 0.8, 0.64, 0.2 times 0.2, 0.04, and then capital A, small a, you have 0.8 times 0.2 is 0.16, and small a, capital A, 0.2 times 0.8 is 0.16. And then can I say for this one, p squared, AA is equal to p to the power of 2? I can say that. And for small a, I can say q squared. I can say that. And then a, capital A, small a, plus small a, I can say 2pq. 2pq plus q squared plus p squared is equal to 1. P squared plus 2pq plus q squared is equal to 1. This is the Hardy-Weinberg equation. That's the Hardy-Weinberg equation. Application of the Punnet square. Let me right here, right? If I have P Punnet square, PQ, one parent is PQ, the other parent is also PQ. So this parent is P to the power of 2. I hope, no. Well, it's supposed to be P squared. This is PQ, this is PQ, this is Q squared. In your notes, fix it up. I don't know how that happened. That's supposed to be, this supposed to be P squared, this supposed to be Q squared. And then you put numbers in there, 0.8, 0.2, 0.8, 0.2. 0.8 times 0.8, that is P squared, 0.64. 0.8 times 0.2 is 0.16. 0.2 times 0.8 is 0.16. And 0.2 times 0.2 is 0.04. You all agree? And this is the formula. A squared plus 2, this is the Hardy-Weinberg equation. A squared plus 2 capital A small a, capital A small a, plus this one square, p squared. All of this population, all of that population is equal to 100%. 100%. For example, a equal 0.8, small a 0.2, 0.8 to the power 2, 2 times 0.8 times 0.2, plus 0.2 to the power of 2, all of that is equal to 1. 0.64 plus 0.32 plus 0.04 is equal to 1. This can be expressed in a Punnet square as that. Okay, now, I'm saying in a city of Lodi, there's a mountain house, 10,000 people live, right? Somewhere, Lodi, 10,000 application. All of I said, what does it have to do with anything, Amir? Well, it can predict future. All of this can predict future. Okay, so 9 out of 10,000 people have a certain disease. Cystic fibrosis, whatever disease you say. Okay, but it has to be a genetic disorder. It has to be a genetic disorder. 9 out of 10,000 people have this disease. Now, in a city of Lodi. Now, I want to know, the question is, I want to know how many percent of the people in city of Lodi carrier are capital A, small a. They are carrier for this disease. Do it make sense? This is what I want to know. The people who are not carrier, I'm not interested in them. I don't want to move into that town, for example. The people who already have the disease is 9 out of 10,000. Do it make sense? I want to know how many people in that town are like that. Do I want to move into that town and get married with somebody in that town or not? Do I make sense, everybody? I want to know how many percent are like that. I don't know what other lame language I can put it so you can understand the matter. What is the application of Hardy-Weinberg equation? Okay, so Q squared, that's what this is. Q squared is 9 divided by 10,000. If you want to take out your calculator and check my calculations, you can do that now, but during the exam you cannot. 9 divided by 10,000 is 0.0009. Equal to AA. That's the population of the town who have the disease. Then Q is square root of 0.009. 3 zeros. Is equal to 0.03. So A or Q in this example, A equal to Q in this example is 0.03. So I know my equation, and P is 1 minus 0.03 is 0.97. And we can substitute in the equation. Equation is P squared. You remember this? P squared plus 2PQ plus Q squared equal to 1. You remember this? I already proved it for you, the equation. So P squared is 0.97 to the power of 2. 2PQ multiply 0.97 times 0.03 plus 0.03 to the power of 2 is 100% of population of Lodi. That's 100% of population of Lodi. Okay, therefore 6% of population is capital A, small a. How did I calculate it? 0.97 times 0.97 is 0.94. 94% of the population of Lodi are capital A, capital A. 0.97 times 0.03, then times 2 is equal to 0.0582, which I rounded off to 6. This is rounded off to 6, and that's the population of the Lodi that are carriers. And then of course 0.00009% of the population of Lodi are having the disease. Takes a look, bring some scratch paper. I will give you a scratch paper. Don't bring anything. Just Scantron. And a pencil. And your brain. Yes, I should not take. A lot of times I joke around. I'll joke around and say, you know, I'm allowing you to take this test or quiz with open eyes. This guy wanted his black belt in karate. They put him in a room. True story or not, I don't know. I've heard it from a friend. True story. They released 7 birds in a room, and they gave him a sword. He had to cut the head of those birds in that room while they were flying, of course, with his sword, blindfolded. Only 7 strikes. He could not go, hoo, hey, hoo, ha, hoo, he. No. 7 strikes, blindfolded, then he would get your black belt. So when I say you can come and take my tests with open eyes, I'm doing you a service. It could be like that karate exam, for black belt. Closed eyes, 7 birds, and 7 strikes with the sword.
Is that ethical?
They did it. I don't know, ethical or not. Read some of the Chinese old proverbs, old stories. You'll come across that. I am way in the future. You take my exams with closed eyes. Okay, so total is 1. In other words, about 0.06 or 6%, I'm running it off. 6% of the population is carrier for the recessive allele. Mother Teresa said, last sermon of the semester, Mother Teresa